Why don't we make a saturated hydrocarbon with 2 carbons? 1, 2. We'll start by bonding them together. Now we have to add hydrogens until both carbons are happy. Since carbon makes 4 bonds in this configuration, these are each going to need 3 hydrogens. 1, 2, 3, and then 1, 2, 3. There we are. A 2-carbon hydrocarbon chain. This here is called ethane. 2 carbons. Before we go on and my hand falls off from drawing all these little hydrogens, these chains, saturated hydrocarbons are grouped in a family. They are called alkanes. You can hear it in the word methane and ethane. They all have that little suffix, ane, just like alkane. Actually, this has to do with how many carbons are on the chain, their prefix. Here are the first 6. These are some alkanes. On the left we have a number of carbons in each chain, and on the right we have the prefix before the suffix, cane, in naming it. So we already did methane, 1 carbon, and 2 carbons was ethane. Next is 3 carbons, that's propane. 4 carbons is butane, that's but, not but, it's not butane. 5 carbons is pentane. 6 carbons is hexane. And I didn't have any room to fit the others, but I'll go up to 7, heptane, 8, octane. You probably heard about that when you were pumping gas, the octane rating and stuff. And 9, nonane. But those are really high numbers, and, well, especially anything beyond that just gets kind of trivial, so we're going to start with just up to 6 or so. Some of these prefixes sound kind of like their number, but some you may just have to look up, unless you're like an ancient languages expert or something. So let's draw the next one, propane. I already drew it here in all of its polyatomic glory, each little hydrogen. Now, if you've been drawing along with me, you've probably felt your wrist get a little tired drawing all those C's and H's, or at least you've noticed me complaining about it. If you haven't, maybe you just draw hexane a few times in the full atomic form, and so you can appreciate my grief. So, since this is a pattern, this pattern of hydrogens bonding to carbons in this 4 configuration in a chain, organic chemists made a shortcut. It's a shortcut that makes propane look like this. A lot smaller. So how is this propane? Well, the way you read this is there is 1 carbon where your pen starts, and everywhere it changes direction. Also, where it ends. That's 3 carbons for 1 where I start, 1 where I change direction, and 1 where I end. It's also assumed that each carbon has all the hydrogens it needs to be saturated, or happy. At the ends it needs 3. There's 1 bond you see, and for each carbon to have 4 bonds, there has to be 3 we don't see. These are the 3 hydrogens that we assume are there. That means this carbon in the middle, since there are 2 bonds we see, it needs 4 bonds total. We assume that there are 2 hydrogens there. 2 we see, and 2 we don't see. I know you may get frustrated with this shorthand at first. It seemed kind of sloppy and a little careless, but remember, this whole thing was invented to make your life easier, and soon you won't even have to think about it. Let's do some more alkanes just to get the hang of things. Butane. Not butane. That's 4 carbons. Let's draw it. 1 carbon where you start, 1 carbon where you change direction, another for a change in direction, and 1 for where you end. So we're done. 1, 2, 3, 4. That's CH3, CH2, CH2, and CH3. The carbon skeleton is made up of 4 carbons, and when I say that, I'm talking about just the carbons, no hydrogens or any other atoms. 1, 2, 3, 4. And you may not understand this now, but there is a reason why I'm drawing them at this funny angle. You almost have to just pretend that there is an axis here at each point, and you are making these angles congruent. We'll cover that why later on, but it's very important to get the hang of it. You're going to want to make that a habit. This is the happy angle. I think it's 120 degrees. Whatever. Moving on. Let's do hexane. 6 carbons. 1 where I start, 2, 3, 4, 5, and 6 where my pen landed. Hexane. I know. Let's do something fun. What if we were to make a ring? What happens if we connect hexane head to tail? So we have 6 carbons, but instead of forming just a chain, they form a ring, kind of like a snake if it were to swallow its own tail. 1, 2, 3, 4, 5, and 6 where I ended, and I'm going to connect it here. This forms a hexagon, kind of what you'd expect. Hexane forms a hexagon. This has a special name that's not just a hexagon. It's actually called cyclohexane. If you want to make a ring out of an alkane, you just add the prefix cyclo. Cyclohexane. How about a ring with pentane? 5 carbons. Cyclopentane. 1, 2, 3, 4, 5. And then I connect them. It makes a pentagon. Cyclopentane. You could have figured that. See if you can figure out a few more on your own. What do you think cyclopropane would look like? That's 3 carbons. I'm going to give you a hint. It's a triangle. What about cycloheptane? 7 carbons. It's not really, I forget what the shape is called, but it kind of forms like a barn. But you can try that on your own if you want. It's pretty straightforward. But why don't we try something else? Let's try adding a double bond in the middle of a regular old hexane. What would that look like in this crazy line notation? It's actually a lot easier than you'd think. We're going to draw 1, 2, 3, 4, 5, 6 carbons. And why don't we just slap a double bond right in the middle? We just double up on a single bond. It's just another bond. What about the hydrogens? Well, I said that in this notation we just assume that every carbon has all the hydrogens it needs. Instead of 2, these 2 carbons just need 1 because there are 3 bonds we see, so we assume that there's 1 bond we don't see, CH. I'll draw them here just so you can see them at first, but you'll rarely see them drawn out. So, what if you have something in the middle of a chain that's not a carbon or a hydrogen? Something like oxygen. Well, I'm going to show you an example. This is ether, or lighter fluid. Ether has an oxygen in the middle of 2 ethanes. Here is what it would look like. 1, 2, break for an oxygen, and then continue counting. 1, 2. 2 carbons on each side, and an oxygen in the middle. It all makes sense if you just break it down with what you know. Here is ethanol. Everclear, essentially. We have a 2 carbon chain, and then an O and an H. Here's what it looked like. 2 carbons, 1, 2, then an OH. You just assume these carbons have all the bonds they need, and then you just draw on what's not accounted for. How about one more? This might be kind of intermediate, but I think you guys can handle it. I get the feeling you're pretty sharp. You biology types may have known the mantra C6H12O6 to signify glucose. Why don't we draw glucose and see if all these molecules are there. We're going to look for 6 carbons, 12 hydrogens, and 6 oxygens. I'm going to go ahead and give you the basic skeleton of glucose. It's a ring. This is a ring made of 5 carbons and 1 oxygen, kind of combining everything we've learned so far. Then we're just going to have a bunch of stuff sticking off each piece. So let's draw an easier version with the notation we learned. Here's the oxygen, then a carbon, a carbon, a carbon, a carbon, and the last carbon to finish the ring. Then you have some OHs sticking off of some of these. Here, 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 and here. Then there is this one with another carbon jutting off, and off of that carbon an OH. So, see how it looks a little prettier than this one I drew over here? We have the ring that's interrupted by an oxygen, so we just draw that in there, like the atom. And I'm sure so we were looking for C6H12O6. You can go ahead and count them on your own time, but assuming every carbon has all the hydrogens it needs, and also counting the H's in the OH group here, I'm pretty sure you'd find all the atoms. So, you may feel a little scared right now, and rightfully so. You've just ingested a lot of organic chemistry, at least like 3 lectures worth. Don't worry. If you're still a little shaky figuring out structures, especially that last one, that was probably, may have been a little much, but like I said, I get the feeling you guys are sharp. This will all make sense soon. We still have to learn functional groups. It's going to make drawing these a lot easier. So, in the meantime, I'm going to give you a little bit of homework so you get comfortable with drawing structures. See if you can look up some of these on Wikipedia.